is heat energy. Here we're going to be talking about and building our concept together. Okay, us together will discuss on what's called the first law of thermodynamics, and we'll break down each and every concept to understand what the heck it is. Okay, now after from previous sections, what we learned is that we can conclude that, let me just write it down. After what we learned from previous section, we can basically conclude that whatever amount of heat that goes into the system, okay, that goes into the system, you're never ever going to be able to be like get more than what the heat you put in. Okay, that's reasonable. Think about it. It's always true. You're never going to get more heat what you put in. Okay, so you can remember this over here to understand the basic concept of whatever we learned in our previous section. Okay, now think about that. Rather summarizing the whole section of this, let's go ahead and jump into it. Now, the first law of thermodynamics, think about it. Do you know that thing, first law of thermodynamics? Well, no, but it turns out that most of the physics isn't really hard. Most of the physics is basically very easy if you understand the concept over here. Likewise, if you understand this concept over here, you'll understand the first law of thermodynamics very easily. So let me just go ahead and erase this, and you could have copied that down to make yourself remember what we learned. Okay, now first law of thermodynamics. Basically, the first law of thermodynamics says that it's a pretty small equation with 3 variables, and it basically says that the heat is equal to the work done plus change in internal energy. Okay, now let me focus on this. There's one variable here, one variable here, one variable here, right? Now, we talked about 2 variables out of 3 variables in our previous sections. If you don't know what this variable stands for, don't get too confused, because here we'll be talking on it. Okay? Now, basically, this term, what it means is that, let me just write it with blue marker. Q, if you don't know what Q is basically heat, okay, that is being added to this system. Okay, work W basically stands for the work done by system. Okay, now it turns out that we talked about Q, which is heat added to a system, W, which is work done by system. Now U is completely different concept to us. It's a new concept to us that we'll learn in this section. That is the first law of thermodynamics. Now, the first law of thermodynamics has this equation over here, which includes change in U. And without knowing what U is, we can know that if a variable has delta in front of it, basically means it's a difference in the change in U. Okay, as you guys can see. So it's basically trying to tell us that final U minus initial U, that is what gives us the change in U. Okay, now U basically is the internal energy. Let me just write it over here. U is basically the internal energy. Okay, internal energy that is present in the system. Okay, now to summarize this up, if you don't understand what this means, it's basically temperature of gas that is being going up. Okay, the temperature of a gas that is basically going up, or likewise you can also say the temperature of gas that is heating up. Okay, now let me just move aside from this board so you guys can focus on the equation over here. Okay, the equation that I put on the board has only 3 variables, 1, 2, and 3, as you can see. Now, I mean, how complicated it could be to actually understand the concept? Well, like I told you before, First Law of Thermodynamics isn't really hard to understand. All you have to do is recall the concept that you learned in previous sections with me. We discussed the concept on previous section. All you got to do is focus on those things that you learned, write down in your notes, and when new concept pops up to you, you basically will understand this, okay? And I hope eventually after this discussion you will understand it. Okay? This equation, let me tell you. This equation that you guys see on the board, okay? If you know the use of this equation, hopefully after this section, if you know the use of this equation, you know where the heat goes into the system. Okay, whatever the amount of heat you put in, you can calculate or you can predict how much amount of heat is being transferred, where is it going, where is it being transferred. You can answer all those questions by yourself if you know the concept. Okay, now the very important concept that lies in this equation is that the heat is being trapped between the work done and the internal energy. Okay, now I want you guys to think about it, because the formula that you see up on the board doesn't have only one use in nature, and I'll show you the different uses, okay, different types of uses after we learn the basic concept at least. But what I want you guys to focus is on that this equation has very vast area of use in which you can predict where the heat is being transferred. If you have a system, if you apply the heat that is put in actually goes in the work that the system is doing, and the internal energy of work. Okay, we'll discuss every single thing on this, but as you guys can see, when the heat goes into the system, it's being trapped by 2 variables, 2 substances, that is the work done. Okay, as you guys can see, the piston does work, okay, goes up and down, it does some work that is done, it does some work on the system, so heat goes into the piston, okay, and the internal energy of the piston that is being applied, okay, so heat is being, basically what's happening is that heat is being trapped between these 2 substances over here. Now that we have understood the whole concept of this equation, now let's go ahead and talk about what the U basically is. Now here I'll be writing down the concepts of U, and I want you guys to focus in, because when I write this stuff down, it makes me pause myself, calm down myself, and make you guys remember what the U basically is. So let me go ahead and erase the board to understand what the U basically is. Now, okay, U. The equation that we had is basically Q is equal to the work done on the system plus the change in U, right? Now here we'll be talking about change in U. So let's point that out. And it's an important concept, so put a star or whatever you call it next to it. Change in U is independent. It's independent of path, even though W over here and Q over here. Let me just write in different colors so you get the concept. What I'm trying to say is that W and Q that are W and Q are basically dependent, okay? Are dependent on the path. So the change in U is independent of path, even though W and Q are dependent on the path, okay? So you can tell right off that when you know the concept of U, you can totally tell that Q and W are basically dependent on the pathway that is being going on or flowing on or anything that it does on the system, okay? It basically depends on the type of system that you choose, okay? So W and Q are dependent on the system, okay? They're being dependent on the pathway. But the U over here, which is the internal energy of the system, it's not dependent, it's independent of path. It doesn't care what the system is, it's always going to be the same. Okay? Now, let me go ahead and explain you what independent and dependent values basically mean. Okay? Now, what I want you guys to do is basically recall that, remember those PV diagrams that we had? It had some pathways and things like that to it. Okay? And PV diagrams are said to be dependent on the pathway that it chooses to go on, okay? Wherever it goes on, you have a PV diagram over here. It basically goes to the first and then goes down, volume increases, pressure decreases. We talked about all those concepts in our previous section, okay? Same concept are applied here. Nothing is being different. There is no different thing. Physics is all related to each other, okay? If you don't know fundamental physics, it's going to be hard to understand this physics because it's like learning calculus without having the base of algebra. You guys can tell that it's going to be very, very difficult, okay? So U over here is basically internal energy of the path. So U internal energy of the path. Okay? Now, there will be tons of different paths. Okay? In system, you have different paths that the work done or the heat that basically flows has many different paths. But the internal energy, okay? The internal energy that we learned in previous sections that has PV diagrams. Now there will be tons of different pathways, and we can tell after what we learned in the previous section about the PV diagrams, okay? Now the point that I'm trying to make here is that the Q and W will have different values, okay? Each and every single time they will have different time because they are being dependent on the pathway they are being choosing, okay? Each and every single time, if you have different systems, okay, and if you take the heat and the work done, they will have each different pathways every single time. But the internal energy of the pathway doesn't depend on the system. It depends on how much the heat that is being applied to it, okay? So it doesn't really depend on the system. It depends on the amount of heat that is being produced to the Q, okay? So the internal energy, that is the change in U, is said to be independent of the path, okay? Now what happens is that, let me do some math over here. Let me erase this. Okay? When you subtract Q and W, you will get U as the answer. That is, if you have, when you subtract Q from W, you will have your answer as change in U is equal to Q minus W. Okay? that basically means that if you subtract W from both sides, you'll end up with this answer over here. Okay, this over here comes over here. Okay, but you can also write it as change in U is equal to Q minus W. Okay, and then you can convince yourself. Okay, so therefore, what I can memorize that the U, that is the internal energy, that is the atomic motion of the gas, which is always going to be same no matter what. Okay, and congratulations, because you just answered the question, which basically will be on the exam or quizzes. That is the question that which values over in this equation are dependent or independent. Now we know that Q and W are dependent and change in U is independent. Okay, so we just answered that question. Okay, now before we move on, okay, as we move on into other hard concepts, basically this, what I write over here, basically introduces to the terms and the definitions of what we talked about. Recall that I said there's vast nature in which you can use the change in U. It's not just used in one single system. You can use it in many different types of systems. So here we'll be talking about many different types of systems. So, but before we move on, I need you guys to introduce you to the definitions. Okay? So the first definition that we'll have up is isobaric. Okay? So terms, and these terms you can find it in your textbook. Okay? So the first is isobaric. Okay? Basically it means that iso basically means constant. Okay? So, and baric basically means the pressure. So you can say the process which is at constant pressure. Okay? The second is volumetric. Okay? It's the process. We call that iso basically means constant, and volumetric basically means the volume. Okay, it's very basically understood. Is at constant volume. Okay. Third, adiabatic, which basically means the process where no heat is transferred. And we can tell that when no heat is being transferred, there is basically Q is equal to 0. So we can write this. Q is equal to 0. Okay, because no heat is being transferred. If no heat is being transferred, then basically Q is equal to 0. Okay, it's not that hard to understand these concepts. The fourth is isothermal. Recall from the first section that I told you guys that thermodynamics basically means thermal, heat, temperature. Okay, thermal basically means the temperature, and iso means constant. So we can tell that the isothermal is the process that is at constant temperature. Okay? Now, what we are going to do after learning the equation, okay, we are literally going to make or held each of the variable constant, okay, which we said this over here is basically being constant, that Q is basically going to be 0, okay? So let's talk about the first process, the first system, okay? So we'll talk about the first system, okay? Now let me go ahead and erase the board. Okay, the first system, I'm just gonna name it A. Okay. Okay, the first system, we know that we said adiabatic system is basically when Q is being held to 0. Okay? Now, it's this system over here is basically, I'm going to tell you the features of this system, okay? And the feature of this system is basically it's being well insulated. And what is it? It's basically a system, so well insulated system. Okay? The second point is it occurs very fast, okay? It's very, very fast. Or you can tell, okay, or occur very fast, or no heat goes in nor it goes out or comes out. Okay? Basically, we have a Q which is equal to 0, and how would the equation basically look like is basically we learned that the equation is basically said to be, and now let me just, Q is equal to the work done plus change in U, change in intern. This is what the first law of thermodynamics tells us. Okay, and if we know that Q is being held 0, so we can basically say 0 is equal to W plus change in U, right? So basically, if you turn the Q over here, if you put the Q over here, W I mean, you basically will get negative W is equal to the change in U. Okay? Or the change in U is equal to negative W. So this is the equation that you guys need to remember. You see how from one equation we are ending up with different equations. Okay? So this equation is very important, and I want you guys to remember this. Okay? When you have this system over here, which is a well insulated system, which occurs very fast, or no heat goes in or comes out. When this is the case, when Q is equal to 0, basically no heat goes in nor it comes out, Q is equal to 0. Q is basically equal to the work done plus internal energy. 0 is equal to work done plus internal energy. So basically, if you rearrange the equation, it would basically look like this over here or this over here. But more consistent people use the equation is basically this over here, which is the change in U is equal to negative W. Okay? Now, what we can conclude, okay, let me just erase this over here. What we can conclude out of this process now, the equation that we got is basically change in U is equal to negative W, right? After we concluded that, we can also conclude that of work and work done by system, okay, it must be lower than the internal energy. Why? Because since there is a case, since Q is held to be 0, okay? So we can conclude this after what we learned over here, okay? Now, basically what it's trying to tell us, and I'll show you by representing a diagram, okay, after I erase the board. Here you have a diagram of adiabatic, okay. In this diagram you have a container, some gas present inside the container, and you put something over it, okay. And let's say if this were the beans, and the beans, what's happening is that beans is pushing down this object, which is causing the gas to compress, okay. And when it's being compressed, when it has low pressure, we already said that temperature goes high. Alright, so at this time, this particles, which we call it bean or anything, pushes the piston. Let's call this as piston, okay. It pushes it down, okay. And what's happening is that if we take out the particles from here, like take one out, take two out, eventually what's going to happen is the pressure is going to increase, and when the pressure increases, the temperature decreases, okay. So the gas no longer is hot, it cools down, okay. So the heat is being subtracted, okay. Why? It's because when we expand the container, the molecule itself is going to push itself up, okay. That is the reason why. And this is the first system of adiabatic, okay. We'll move on to a second system in which we'll have a constant volume, okay. So let's go ahead and jump right into it. So the second system is known to be second system, which is B, okay. It has a constant volume. It has a constant value. Since the volume doesn't change, the work done is equal to 0. It's kind of acceptable, because if someone were to have constant volume, that means that the initial volume, whatever you have, is equal to the final volume, okay. The initial volume that is initial is equal to final volume, and when you have that, this is the case over here. So when the volume is constant, there's basically no work done. No work is done. Basically, we can put this into equation as W equals 0. You see how what path are we going on to? Okay, so let's go ahead and talk more about the constant volume. Okay, right. Let's go ahead and write each and every points down. So for the constant volume, we said since the volume, okay, since volume doesn't change, okay, work is equal to 0, because no work is done. No work is done. And the example for this is basically if you have a piston. If a piston is just sitting there, okay, it's just sitting there because the volume never moves, okay, volume never changes, piston just sits. Same with the diagram we had. In the diagram, what we did is basically took out those particles, right? If we weren't to take those particles out, the piston would stay at the constant place, okay? No pressure is changing, no pressure of the gas is changing, no pressure of those beans or the particles are changing. So it's an example of constant volume, okay? And basically what we learned is Q is equal to W plus change in U, right? And that's the first law of thermodynamics that we learned. Now, basically, you have a Q. You know the W is equal to 0 because no work is done, plus change in U. That means if we exclude this part over here, Q is equal to change in U. The heat is going on to the internal energy. Okay? So this over here is the main point. This over here is the main point. This over here is the main point. Okay? Now, you don't need to remember this thing. All you need to do is remember this thing, and you know the equation, and you basically can solve for this equation over here. Okay? So there is no point of remembering this thing, but if you do, it's awesome. Okay, so since we said that the energy is conserved, okay, and when you basically in the adiabatic, okay, when you have a volume that when you take off those particles, the energy is being conserved. And now that we know that energy is conserved, and we can put that energy into the piston, okay, or any other system you like, okay. Well, the energy is constant, right? So therefore we can say that energy goes into the internal energy. So the heat over here basically is equal to the internal energy, okay? So the energy basically goes into the internal energy. You see where it is going, okay? If you have a constant volume, if the energy is being going into the internal energy, okay? In adiabatic, the heat over here is being 0, and 0 is equal to W plus change in U, which we said is equal, that comes out to be negative W is equal to change in U. Okay? That's basically it. Okay? So there's no energy going in it. The energy is being conserved. That's what we can say. So let's go ahead and talk about more on the constant volume. So we are still on the constant volume, okay? That we can also say that any heat added to the system, okay, goes right into increasing the internal energy of the gas. Well, that's basically true, because if you were to have Q is equal to change in U, that's what we have for the constant volume, right? So if you have some number of S representing the heat energy, and some number representing the internal energy, it's perfect that if you increase the heat energy, you're basically indirectly increasing the internal energy as well. So we can also conclude that any heat added to the system, okay, goes into increasing the internal energy of the gas. Because no work is done, work is equal to 0. We don't care about the work because no work is done. We only care about the heat that is being produced or increasing. That is basically equal to the internal energy. Okay, now this process, the next process that we come up is what it's known to be a cyclic process. Okay, you may have not heard of it, but you know a lot about it. Okay, and you talked about cycles. Okay, not those bicycles, but how the nature works, the cycles, raindrops, vaporization. You see, it's cycle, right? You learned about that. Same with the cyclic process. That's, see? Cyclic process. Okay? Now, cyclic process, like I told you, is basically like a cycle, okay? Which happens again and again, okay? I kind of touched on this topic in my previous video, okay, in that PV diagram, that if you move from initial point to a final point and make your way again to the initial point and make your way again to a final point, make your again to initial, again to, you have initial point, final point, okay? This is the PV diagram. You go over here, you go over here, you go over here, here and here. If you make your way, go over here, here again and again, you're going back and forth, back and forth, back and forth. It's like running on those fields. When your coach makes you say run 2 laps, well, basically you're going in cyclic process again and again from the starting point to the ending point, which is basically the same. So from the initial point to the final point, cyclic process, okay? So let's go ahead and talk about it. Okay, after interchanges, okay, this over here, let me write in another color. After, okay, it interchanges of the Q and W, the work done on the system, okay, returns to its initial state. Okay, that basically means that the change in U is held to be 0. Okay, and you have this equation over here, you write it down, you replace the internal energy with 0, and at the end of the day what you get is basically the equation that you need to remember, which is Q is equal to the work done. Okay, and one more information here is that the change in internal energy is basically held to be 0. Okay, it's basically this nice pretty thing that if you were to have a system like we did in a PV diagram, where we drew stuff and we described the PV diagrams of those systems, okay, and if you, it's really not that hard to understand. This sentence is saying that after interchanges, after from the one initial point to it goes to the second point, which is the final point, okay, and when it returns to initial point, okay, it basically is the cyclic process. Like I told you, those lamps, you run around, running out, initial point to final point, you go over here, no matter how much you need to travel, you go to a final, let's say for example, you were to go to your aunt's house, okay, and when you go to your aunt's house, let's say she lives 3 miles away from your house, okay, you travel 3 miles, right from the house, right from your house, it's known to be initial point. Her house is what you're trying to go for. It's the destination point. So it's denote that as the final point. And when you go there after, let's say, days, like 1, 2, 3 days, you stay there and come back again. Soon you're going to come back again. You see the process, you go from initial to final, and then you come back again. And sooner or later, you go back again, you come back again. That's basically a cyclic process, going through reverse and coming in again and again. Okay? And the energy you put into the heat is basically goes purely into the work done, as you can see by this equation. The energy of the heat that you put into the system goes right into the work done. Okay? And you can't get any more work done than you put into the energy. So let me just write it down if I'm confusing you. And notice that you need to write these points down along with me, okay, because I'm gonna right after I write it, after sooner or later I'm gonna erase it, okay, because I don't have that much space to just write all those points down. Now, another important point that I need to tell you guys is that you can't, never can get more work, okay, than energy you basically put in. Okay, and that's basically it. Okay, so if you were to increase the Q, basically what you're doing is indirectly increasing the W. Okay, because Q, the energy, heat energy, is equal to the work done. Okay, if you're increasing this over here, is basically the first law of thermodynamics says that it has to be equal, okay, to work done plus the internal energy. And the cyclic process has the internal energy of 0 because, okay, because it's going back and again, back and forth, okay, cyclic process. That is the reason why you have no internal energy, so it's just concluded as 0. It's like adding 0 to a number. It gives you, in return, at the end of the day, it gives you the same number. It's basically the identity, you can call it. Okay, that's what we learned in algebra. So Q is equal to W. If you were to increase the Q, you're basically increasing to W. Okay, let's talk about now. We have learned 3 types of process. Now let's move on to our last process, which is known to be free expansion. Okay, so let's go ahead and jump right into it. And you can accept what I said before, that this over here has basically many vast areas where you can use the first law of thermodynamics. And if you haven't noticed, we're basically using the first law of thermodynamics again and again. But this type of process gives us some clues, such as the constant volume gave us the clue that it has the constant volume, okay? That means the work is not done, okay? We don't care about work in the constant volume because it has the constant volume, okay? So the Q is equal to internal energy. You see how the equation changes as the process are changing, but the equation remains the same, okay? So our the fourth, which is D, let's call it D, that is the free expansion. Okay, in free expansion, let's say you have let's say you have this over here. Okay, you basically have this type of object. Let me just go in and let me draw a nice little object. Okay. You'll see what I'm doing here. Okay. Here basically you have a gas. Okay. You basically have a gas over here. This part over here is basically vacuum. Okay. And you basically have tied the knob in the middle so the gas doesn't flow over here. Okay, this doesn't have anything in it, it's vacuum. It has vacuum in it, and this is present with the gas. Now what's happening in free expansion, that if I pull this knob out, you'll make yourself notice that this over here is going to spread out, okay? It's going to increase the volume because here you have some type of volume. Here, as the gas moves over here, it has free expansion. It increases the volume, right? Now, like we said before, that when you increase the volume, the heat is basically zero, and when it's basically in the same system, so the work done is basically zero. So we don't care about heat, we don't care about the work done. So what's happening is that, let's take out the knob over here. Okay, you take out the knob. The gas basically spreads out. Okay, the gas you have spreads out over here. Okay, not the best drawing in the world, but I never say I was the artist. So basically you have let's go this line up. You basically have a gas over here, spread it over here, gas over here. So it's increasing its value, right? And we can conclude that since it does that, Q is equal to 0, no work is done. This is an important concept, you need to understand this. Okay, now let me just erase this and teach you guys the concept on how the equation would look like. Okay, so basically you ask, the first law of thermodynamics is the Q is equal to W times change in U. And we know that Q is 0, so let's replace it with 0, is equal to W is 0 plus change in U. Basically what's happening is that you can conclude to yourself that change in U is basically equal to 0. Okay? So the internal energy for free expansion is basically 0. Okay? So far right now we talked about 4 types of processes.